So I want to talk a little bit about the tool chain. Since we want to generate the code, so it's things that you don't want to do repetitively, so we can do code generation. We can do this because all the things in 1 iota, that's a little bit glanced over, 1 iota, that has definitions in Swagger. And the definitions in Swagger means that they are machine readable. And machine readable means that we can reuse them. We are already using them to pull into the specs, so it's the source of our specs. We are already using it in the CTT, the test tool, so that we can use them to validate if something is correctly. And the third thing that we are now introducing is that we also are using these definitions to generate code. And basically the Swagger defines which operations there are, which URLs there are in the device, which operations there are, the schema that belongs to the payloads of those definitions. And we also have an example of the payload to make it a little bit more understandable. And since we're doing RESTful interfaces, we also have query parameters, and they are also defined in the Swagger definition. So all the information to create an implementation that handles kind of things, we already have that inside the definition of Swagger. So, since we did this in various stages, we have all the Swagger definitions in 1 iota, but they are all separate definitions. For each resource, we have a separate file. But we don't want to create a separate device. We want to collect what we want to do, and that stage we call device builder. That's just saying which resources we want to use in the device, which URLs they should have, and we want to generate one big Swagger file of that one. And that Swagger file, we run it to the tool Swagger to X, and that generates the code. And that code generation is done based on templates, so if you have another code that you want to generate, we can do that by means of that tool. And of course, you need the compilers to make a real executable. So the tool chain itself, it's nothing more than a set of Bash scripts and Python scripts, so that it's one chain. The script installs all the necessary repos for you. It installs the packages that is needed for Python 3. And it's all based on Git Bash, so it runs on Windows using Windows Bash, but also on a Linux machine. And as you will experience, also on the Raspberry Pi. So the device builder, that's the tool that just make sure that there is one big Swagger file and that is then being used. It has additional features, so you have to define which resources there are, and it also has options to remove properties that you don't want in your implementation and renames paths that are by default already in the Swagger file to match what you want in your application. And to make this happen, there is just a very simple JSON input file that describes that file. Swagger to X, it's a template engine, so anybody are familiar with HTML template, it's using under the covers Jinga 2, maybe you're familiar with those kind of things. I don't know, but it's basically just looping over all the information in the Swagger file, which is just a JSON thing, so that's why we can reuse quite a lot of the templating technology. And then it generates the code by means of the template. Sounds easy, and actually if you see it, how it's being made, it is not that difficult to do. Since it's a template engine, we are having different templates. The template that we're going to use today is for the C++ API of IOtivity. There is also one for IOtivity Node, so that you can create JavaScript code, and we also have for IOtivity Lite, but we don't have that already packaged up. So the only one that we're going to use today is the C++ API. There's another tool that is, we have CBOR input files for the introspection, and this tool converts the JSON to the CBOR. There is also a file for security. You can't use that tool for the security files because it has different layerings inside. So that's a real difficulty to understand that file. And there will be someone else explaining more about those kind of things, how to use those kind of things. So there is a single script, and it's a very simple way of calling it. It gives you an input file for the device that you want to create. It gives you an output directory, and you also give it the device type as a string. And that's it. And then you just run the script and you will have code. Then the next step is when you have code, how do you build this? So we can generate code, but you have an IOtivity set up, and now you have to work with how that works. So what we did is pre-configure in another script using all this technology so that you can just have a complete IOtivity setup. So it's a GitHub repo. It's called IOtivity Setup, and it installs all the device builders information. It also installs IOtivity itself, and then it creates a few scripts in one layer above, and that gives you the complete chain. And then you just start creating the code and manufacturing the code. So for IOtivity, we're using version 1.3.1 of 1.3. That's the one that we're currently certifying. And also all the other GitHub repos are being set up. So there's one command that you can just issue on the Raspberry Pi, and that is in green. It's a curl command, and it installs all this information for you. So when you execute the command, what do you get? An extensive folder structure on your disk, and the top level that will have a set of scripts which can build, generate, build, and execute the code. And then you just have to edit the code accordingly. So these are the pre-configured commands. I sincerely want to point out that you have to look in what it's actually doing. So it's more like convenience scripts. But to get started, I think it's a very nice way of doing it. The alt-off in this script is the reset one. So since we are using security in OCF, if you want to go back to the onboarding state, then you just run one script that replaces the file that contains all the information of the onboarding of all the security. So that's the one that is being done as an alt-off. We have a few examples of those input files. We will start out with a very simple one, which is just basically a binary light. But you will see that you will have a Raspberry Pi with daughter boards, and we also have example of those files that you can just try it out and start playing with those boards to get up to speed. And an example, this is the complete input file explained. So it has a path. So first of all, it's an array. It has a path. It's called binary switch. The RT value, the resource type that we want to use is the OSC R binary switch. That's the key that's being used to look it up in the 1 iota. Which kind of interfaces we want to use, that are the OCF interfaces. And for this one, it's actuator and the baseline. And there will be a set of properties that we don't want to use in our implementation, and they will be removed, otherwise they will be there. The one in red, is needed for the introspection, because the OSCP for that is implemented in IoTivity as default has additional properties that needs to be mentioned in the introspection file. So it just needs to be in there for IoTivity, and then it will be okay. So it's just not being part of the code that's being generated. So where to find it? It's on GitHub under Open Connectivity IoTivity Setup. So it's just available, and yeah, just use the bash of the curl command to install all the information on your machine. So having code doesn't mean that you understand the code, what it's doing. So we already mentioned we are going to generate code for the C++ API, and it has a main, like every other C++ function, a set of supported functions, and what is really important, it has an implementation class for each resource. So for each path, you have a separated class. Because if you have two light things on your device, you want to control them differently, so you have to have two different ones. I have to mention, we also have a C API, but we are not talking about that in this demonstration. The main, it starts the platform, it registers the device with OSCD, it registers the platform with OSAP, it creates all the platform specific resources, so it instantiates the classes, and then it just loops till you do Control-C or whatever. But it's just a server, so it's just waiting until it needs to end. So the register device, it just sets device informations like device type, device name, data models. So it's just a set of things that you need to set, and that will be turn up. Pretty simple. The resistor platform is the same kind of thing, but then about manufacturer and the platform, system time, a few more of those information kind of things. It's just, if you want to change those things, just go to that function and start changing the strings there. So the IoT server class, it's the wrapper. It just instantiates all the other classes that are being pulled in. So you don't have to touch that one. It will be, if you add a new resource and generate it again, this class will be adapted so that the new one being added is there as well. And the resource class, well, it's just a superclass so that we have to write less code. Just mention it, it's there, it doesn't do much. Okay, the resource-specific class, that's the one that you want to look at because that's the interaction for each resource. So each endpoint has its own class, so you can interact with the hardware. So it doesn't do anything with the hardware. That is the connection you have to make by yourself. It has a set of member variables. So in 1 iota, you have already the properties inside of the payload defined. So it just creates for each property that can be used a member variable. And it also takes from either the defaults in the schemas or from the examples, it also initialize the variables. It's just less work to do. Constructor and destructor, so to get it up and get it down again. It has a get function, which is then mapped to the OCF receive method. It is then pre-populated with all the member variables that it sends out that information. And it also has a post function if that resource supports the post function. And that's similar like the update function. That's a large, pretty large function. Okay, this one I can skip. This one is then pretty large because it does all the checking if a post is valid. So you can supply things that are not valid. Most of the checks are being done already. So there is just an insertion point to update the member variables and then use those values to the hardware. So there are some pointers there to do. So what to do? Yeah, define your own input file and run the tooling and then see what you can get and play around with it. So I will be around this afternoon. Just if you have problems with the code, I can explain later.